Hello everyone. So we're going to start section number 2 under unit 2. In this section, I'm planning to give you a little more information about the motion, including the rotation. So now when I say that, so you remember that beginning of the class, I mentioned that we are talking about the object moving on translational motion. Translational motion means object is moving on or two direction or one direction, or it doesn't matter, but important thing is just moving. So now rotational motion means object will rotate, right? So that can also happen, right? But in real life, object will move with the rotation. So now this is, we call it as the rotational and translational motion together. This is where that we're going to include that rotational part into the motion. So now this will be little complex or the advanced part for your class, but we're going to again conceptually get an understanding how you're going to add rotational motion into the simple kind of problems in your real life. Okay, so now if I share the window that you have it in your Blackboard page, so we know that we're going to work with the chapter 10 in your textbook. Okay, again, it is very conceptual. And let's move into our presentation. Okay, so now here I have a picture about actually what is the translational motion is, and this is rotational motion itself, but together translational rotation will be this concept, right? So now we're going to move into the little bit about the rotational. Rotational, some people call the word is angular, sometimes angular or rotational, same thing. Okay, so now everybody ride the merry-go-round in your life in childhood, or you still go to the merry-go-round. So now if you two people sit in two different places, we'll say this example. So I have you and your friend. We'll say this is you and this is friend. So you two are planned to sit on different places on the merry-go-round, right? So now when you ride the merry-go-round, your friend and you will feel the moving of yourself is different, right? So now that moving that you will feel faster or slower is basically where you sit on the merry-go-round, right? So now if you ride on the merry-go-round all the way somewhere here into closer to the middle, you even don't feel that you are moving. So you feel like you are at resting, but your friend on far away is moving faster. So this faster or slower is not coming from the rotational quantity. This is coming from the velocity that we discussed, or the speed we discussed earlier, that is translational speed of these two people, right? So now, but that has the connection to the your radius that you are sitting on the circle, right? So now we'll say that the red is not going to work in here. Let me change into different color. So now I have this person sitting from here to here, we'll say radius r. But this person is sitting, we'll say 2 times of the r, right? So now because of the larger radius for your friend definitely in your feeling, you know that your friend is moving faster because he's sitting 2r distance. But why it is happening? Because you remember that velocity is basically the velocity, or in this case we can take as speed. Speed is the distance that object travel divided by the time, right? So now we'll think after some time this you make a circle something like this, right? But your friend make a circle something like this. So now the distance you travel, will say you start from here, come back on a circle to same point, What is the distance you travel? That will be the circumference of the circle. That is 2 pi r, right? And time, we'll say it will take a time to complete one cycle as t, right? So now this is for you. So what happened to your friend? Your friend has different velocity. This is your velocity. This is your friend velocity. Your friend velocity, you have the whole circumference, that's this long one, right? That will be 2 pi. Now radius is 2r, not the r. Divide by, do they take different time? No. If they are sitting on the same line on the merry-go-round, they will come back to the same time, complete in one cycle. So now what you see, V finally is greater than V, my friend is greater than you. How much? Twice of you. So why? Because it is double the radius, right? So that's why you feel faster. So nothing related with the angular quantities that we are talking. This faster you will feel because of the linear speed or the tangential speed in this case. Right? So what is the tangential speed means? Tangential means if you move on the circle, this object has the velocity in tangent direction. That's how these two people, if I draw it on my top view, riding the merry-go-round, these are the two people riding the merry-go-round. This is you, this is your friend. Right? So now let's rethink about the angular quantities. Now we understand why they are moving faster, but why do we have a same period to take the one cycle? So that is going with the angular quantities. What that means is angular speed is defined as the how many rotations you can do per second. So basically, that means angular speed units will be radians per second. Radians per second, right? Radians, everybody, I hope, know it, right? If you make one cycle, that means the radian that you are changing from here to here is 2 pi radians. This will be 360 degrees. That's the conversion of the radians. So 5 radians equal 180 degrees. If you complete one cycle, you and your friend both have the same radians you pass per second. So that is the angular speed. Angular speed for your friend and your you or some other friends sitting on the same line will be same merry-go-round. They all have same angular speed. That means they are changing radians per second is the same. Okay, that is called it as the angular speed. Okay, so now if somebody can make more rotation or more rotation per second, that has more angular speed. But all the people sitting on the merry-go-round have the same angular speed because they are doing the same radians per second rotation. Okay, okay. So now again, tangential speed and angular speed to get these two understanding. So tangential speed is the linear speed that measured by using symbol V and units meters per second, right? And angular speed or the rotational speed means you are basically measuring radians per second. That's the units, radians per second, and use the letter, we call it as omega for angular speed. Okay, so now when you have two bugs on the merry-go-round or the rotating disc, they have same angular speed, but they have different tangential speed. That's the main part that we discussed so far. Okay, so now we're going to relate these two together. How we relate tangential speed into rotational speed. So now tangential velocity is equal to the radius of that person that you rotate times the angular speed. We call it as the relation of these two quantities, right? So these two quantities are related to each other. In addition to that, there are velocity, displacement, and acceleration. Those also will be have the connection to angular and linear quantities. So linear quantities, we have linear prefix, but angular quantities, we have angular prefix. But everything that we discuss for the linear quantities will be able to discuss for the angular point of view too. Okay, after you understand everything for the linear motion, understanding for the angular motion, you just change in the prefix, and the way that we calculate or use the equations will be almost the same. Okay, but different symbols and different units. Because of that, we need to be careful with those. So now I'm going to move into the torque, because torque is very important concept that we use every day in our life. Torque is a twist or turn that will produce the rotation. So you know that we have the torque when you lift something. As a simple example, in here, your body is doing a lot of rotation on your joints, right? So if I lift this box, I know that I'm doing the rotation with respect to my elbow joint, right? And then my soldier joint here also do the rotation. And also my backbone joint here also do the rotation. In addition to that, probably your knee joint will do the rotation. And there are many places in our body that when you do the things, we are doing the rotation, right? So now rotational force, we call it as the torque. Torque is the rotational force. In translational motion, we call it as force, but when you come to the rotational, we call it as torque or the rotational force. Okay, so rotational force will be able to calculate by using the formula. I have it in here. So R, F, and sine of theta, you will say as immediately units will be Newton meters. What is the other quantity that we have the units Newton meters? That is work done, energy. Those all are Newton meters, right? Because you are multiplying two quantities, but we had the cosine of theta there. Here I have the sine of theta. That's okay. So now torque is a vector quantity. That's the difference between your work done, because work done was a scalar quantity. And although we have the same unit with the cosine theta, here I have the sine of theta and vector quantity, same unit. Okay. So now, how do we calculate the torque in that concept? So what is the R is? Simple example, you can say for rotational motion, always you should have a fixed point. That is, we call it as pivot point. Pivot point in this object will be here. When you lift in the things, that the joint that I talk, those are pivot point, right? That's where your rotation will happen. So now when I have pivot point in here, when I apply the force here, so now torque in this case will be able to calculate tau used for the torque will be RB distance times FB. So now what is the angle between RB and FB? So this is your RB, this is your FB. Angle is 90 degrees. Again, sine of 90, everybody know, is 1, right? Sine of 90 is 1. Because of that, this will be RB times FB. So that means when you have force and the distance perpendicular to each other, you don't even need to use the sine of 90, because you know that will give you RB times FB. So now RB is the perpendicular distance to the force, then you can multiply the RB times FB. So now here it will be RA times FA. So that's how you calculate the torque. And again, there is a direction that I'm going to talk about the direction in next slide. Okay, so direction, direction will be by conventionally your direction of counterclockwise rotation. We call it as the positive torque. What that means? So counterclockwise rotation is positive work. So now if I have a pivot point here, this example, if I apply the force in this way, we'll say I don't have the bottom force, but I have the force in here. So you have a pen that you're going to push it in here. What will happen to when I push it in here? This will do the rotation this way, right? So now in your screen, you will see the mirror image. But according to my case, this is doing counterclockwise rotation, right? So when you have the rotation in counterclockwise, that means it will do this kind of rotation. That's the direction of the rotation. That is a positive torque, right? So now the force I have it in here also do the counterclockwise rotation. So that means net torque in both cases will be just counterclockwise in this case. But the other case I have here, because of applying the force in this direction, it will move in this way. So that is clockwise to me, although you see the mirror image. So that will be clockwise rotation like this, right? And also the other force I have in here will do the clockwise rotation. You just start with the force direction and then draw a circle in your head. You don't have to draw it on the screen. You just think in your head it is counterclockwise or clockwise rotation. Counterclockwise will be positive value and clockwise will be a negative value by conventionally. Yeah. Okay, so where we have the torque in our real life. So when you ride the seesaw, you use the torque principle. When you balance anything, so that you use in torque principle. And when you lift the things by using your hand, your bicep on the hand will do the some kind of backup kind of rotation to hold that object, right? And when you lift the things, you know that your elbow joint, shoulder joint, back joint, and also knee joint will do the rotation. And it's very important in real life, when you lift the things, you need to be careful with your joints. So this is the best way that you can lift the things. This is not a good way to lift the things that will broke your joints and so on. Okay. And let's move into this rotational equilibrium problem. You remember that in lecture number 3, we discussed about the equilibrium, and also I remember that I mentioned that net tau should be equal to 0 when to make equilibrium, right? This is where that we see that calculation. Okay, so now you see that there is a lady, mass 25, or the girl, mass 25 kilograms, sitting on some distance, and mass kilogram 30, boy sitting 2.5 meters. So now if this boy fix at 2.5 from the pivot, this is where the pivot is, right? So now this girl need to adjust the length or the sitting distance from the pivot point to make it to horizontal. Otherwise, you're going up and down, right? So we'll say I need to make it seesaw horizontal. That distance that lady need to sit, we're going to say it as x. Then we're going to calculate the x, right? So now we're going to use this rotational condition that we have discussed earlier. So net torque equals 0. What that means is, if you write clockwise torque should be equal to counter clockwise torque. This is another way writing the same equation, right? So now you need to think about the three body diagram. Definitely this will be force of gravity, this will be force of gravity for the boy, and there is definitely reaction force or the mass of the your seesaw. There is two forces acting on there, but we are not going to worry about those forces, only worry about the torque in here. That means I need to consider this force and this force that do the clockwise and counterclockwise rotation. So now if I have the boy will do which rotation? You think it is pushing downward direction, that means it will do the rotation something like this. So that will be counterclockwise rotation. So boy do the counterclockwise rotation. How do you calculate it? Force times distance. So I have mass of the boy, G, that is Fg, or force of gravity, times the distance to the pivot point is 2.5. Okay? That should be equal to clockwise rotation. Clockwise rotation is doing definitely by the girl because you have this way. This is the clockwise rotation. Now clockwise rotation will be doing by girl which has MB mass G times X, right? So now you're going to divide by G both sides. Then I need to calculate the X. X will be equal to MA over MB times 2.5. Okay. So now MA over MB, you definitely have the values 30 divided by 25 times 2.5. So you do the calculation by calculator, you're going to get 3 meters. Okay. That means if girl sitting on 3-meter distance, then your seesaw will be flat. Okay. That's how you use the equilibrium condition for to solve this kind of problems. Okay. So now we have some idea about the rotational force. So now we're going to move into the other quantities also, not discuss in detail, but we have the relation of all the quantities exactly same way. Remember that linear speed is equal to the r times angular speed, and also linear displacement is equal to r times angular displacement, and also acceleration, linear acceleration is equal to r times angular acceleration. Angular acceleration is alpha. So it's exactly same concept, but you have different physical quantities. Okay, so now let's move into period and the frequency a little bit. We're going to come back to this again for your next section. Frequency is called it as the number of revolutions per second. As an example, if you write a merry-go-round, how many revolutions, if you time how many revolution you going to complete. This is one revolution. We'll say it is not a second yet, and you complete another revolution. Now it complete to 1 second. So now revolution per second is 2, right? So that is, we call it as the frequency. So now period is called it as how long it will take to complete one cycle. Now you're going to switch on your timer, you complete one cycle. What is the time in the clock now? So that is, we call it as the period. So period will measured by using seconds, right? But frequency will measured 1/2 that is, we call it as hertz. Okay, so frequency and period are related to each other. T is the period that we use, and frequency use the symbol F. They are related. So if you understand one thing, then you will know the other thing. So period is the time to complete one cycle. Frequency is 1/2 period. That's how you calculate it. Okay, so now let's move into about the mass distribution of the object. You remember that on Newton's laws, when you talk about the force equal mass time acceleration. There we consider a point masses that has just a mass. But here, when they have rotational motion, actually how the mass distributed in the object is important. If I need to rotate this object, I can rotate this way. I can definitely rotate in this way, right? So I can probably rotate in this way. There are many directions that I can rotate, different axes that I can rotate. And also the mass that distributed on this object is very important with respect to that axis. So if I'm going to rotate in this case, where my mass is located from my pivot point is important. That we call it as mass distribution. So mass distribution, in another way, we call it as moment of inertia. So moment of inertia is basically how the mass distributed. We will be able to calculate by adding all the masses times the distance to that mass and power 2. So now you can see the units in here. That's the important thing. Units will be kilograms and meter squared, the units of the moment. right? How mass distributed. Take the each point to your rotating point. We'll say this is going to rotate, and then you have mass everywhere. Take the mass and distance power 2, add, and take the mass and distance power 2, add, take the mass and distance power 2. That you need to do through to complete your object, all the mass particles. So that is, we call it as the moment of inertia, because that will affect to the motion. Moment of inertia or the mass distribution will slow down the motion. So this will slow down the motion. That means if you have larger moment of inertia, that will slow down the motion. So that will be the mass distribution. So now how the mass distributed according to the rotational axis is given in this table. So in your class, we definitely use very simple thing to see which one reach first, which one rotate more, which one come have less rotation, and those kind of things. Okay, so simple example that you can think, probably I have the solid sphere here, and I have hollow sphere here. Now you see that the solid sphere, I have this moment of inertia, and thin hollow sphere, I have this moment of inertia. Now you can see which one is greater by using the coefficient 2/5 and 2/3, right? So 2/3 is definitely greater than the 2/5. Then I have more moment of inertia for the hollow shape sphere. So that will do the motion slower than the solid sphere, that kind of things. Okay, so now I will come back to very small simulation that you can find inside your Blackboard page about that. So now how these objects will rotate or how they will land. So simple example is, you can think that the object that I have probably box, sphere, solid cylinder, empty can, and hoop. Since they have different I, that means moment of inertia, they will land in different time. If I start all of them at the same time in this line, so definitely first one reach the bottom will be the box, and then the sphere, then the solid cylinder, then the empty can. The hoop will be the last one, because your moment of inertia is greater in the hoop than the other all the objects. That will slow down the motion. Okay, so now before moving into the kinetic energy, let's take a look on this rotation that you can see it in. If you go to the extra videos, I always suggest you go to the extra videos and check the things I mentioned in there. That will be very good things that you can visualize yourself, right? So now if I go to this video, so you can see there is two objects on the video, right? So two objects I have it in here is one is the, we'll say they have the same mass, right? But one is the hoop, the other one is the solid cylinder. So now if I let these two objects to roll down on the inclined plane, so let's see what will happen, right? So now think your moment of inertia in your head. Hoop has greater moment of inertia and solid sphere has less moment of inertia. That means we are expecting solid sphere to come first, solid cylinder to come first. See? Okay, so that's because of the moment of inertia, right? So now this rotation also will give you energy, because since they have the rotational motion, we need to have a mechanical energy or the kinetic energy because of the rotation, that we call it as the rotational kinetic energy. Now rotational, you remember that translational kinetic energy we calculated by using this formula. Now because of the rotation should have velocity need to replace by omega, that's angular velocity. Mass I need to replace by mass distribution, that is moment of inertia. Now my formula for the rotational kinetic energy will be half times I times omega squared. So now total kinetic energy coming from the translational motion and also from the rotational motion. When this object travel, there is a translational velocity and there is a rotational velocity. These both will affect to the your total kinetic energy. Okay, so now we'll move into center of mass. Center of mass also explain in you the basically translational motion. But when you find the center of the object, that object center, we call it as the center of mass. That also depend on how mass distributed actually, right? So now to get an understanding again in translational motion means object center of mass, this belly button place, is just keeping on the parabolic path. So that is translational motion. But your other parts of the body will rotate around the center of mass. Then this do the rotational and translational motion. Rotational do around the center of mass. Translational motion is motion of the center of mass. That's the difference between rotational and translation. I hope you guys get a conceptual understanding enough for there. Okay, so now another example is baseball bat. When you have the thicker end, you definitely know the center of mass point is closer to the thicker end because more masses are that side. Then your baseball bat will do this kind of motion, right? Okay, so now center of mass point is where your mass concentrated point is. In another way, that is where we draw the three-body diagram earlier. Okay, that will be usually center of mass will be the center of the object if it is uniform object. Okay, so now in theoretically, how we calculate the center of mass? So center of mass will be able to calculate very easily. If I have a MA object in here, if I have MB object in here, now center of mass of these two objects, I definitely know it is in between, but it is not in the middle, it is not in the corner because I don't know what is my MA and MB is. That means my distance center of mass is depend on the masses and depend on the distance to each mass, right? Because of that, we will be able to calculate the center of mass by using this formula. So now it's very important thing is there. You need to do all the measurement with respect to one single point. That point you can define as the origin. You can even define it as in top of the MA, top of the MB, or somewhere else. I define somewhere else in here because I need the general formula. So then I get the center of mass point in here. Then I take the distance to that as x center. Then I can calculate the x center by using MA times XA plus MB times XB divided by net mass. Very simple, right? But sometimes your XA and XB will be negative according to the point that you choose. In this case, I have both are in positive coordinates, right? But if you have something in negative coordinate, then you definitely need to use the negative value. But in your class, mostly we use the positive cases. But if you have many masses, what you're going to do is still the same process. You keep adding mass time distance and then divide by the net mass. So this is true for any axis, x-axis, y-axis, z-axis, it will be exactly same way. You just need to use the coordinate distance x and y accordingly. Okay, so to find the center of mass in your home or your laboratory will be very simple. If we need to find the center of mass of the paper that I have it in here, to find the center of mass of the paper, what you can do is you're going to use the paper and then you're going to hand that paper but by using thread or by using your hand, and then you're going to draw the line that is vertical in your paper. So you're going to draw that line, right? And then you're going to hang the paper again by using different points. Which say I'm going to hang the paper by using this point, and then you're going to draw the vertical line in here. So now after I draw the vertical line in there, you're going to see they will cross each other in some point. That will be the center of mass point for this object. So wherever you hang this object, that line will go through the that crossing point for the object. That will be the center of mass point of the object that you can easily find it out. Another way that you can find it out is the basically by using a pivot point. So now by using pivot point, you will be able to find the center of mass point. So I have the pivot point in here. Here is my pivot point. So now I have this bird. I can keep this bird on the pivot point by using the beak. So now where is the center of mass point of this bird? So it is his beak. You see that? It is balanced in that point. That means although this bird body is in that side, but because of the feathers has more weight, so he can balance himself by using the beak. So that is the center of mass of this bird, right? So now if you think about the center of mass of the donut, donut has the center of mass in the middle of the hole, although you don't have the donuts in the middle of the hole, right? The material is not inside the middle of the hole. So that's the center of mass that you can easily find. We can easily understand on the objects. Okay, so now let's see that. Okay, let's move into the actually last concepts, angular momentum. You remember that we discussed about the linear momentum in translational motion. Similar to that, angular momentum also there when you have angular motion or rotational motion. So angular momentum, linear momentum, you definitely remember mass time velocity, right? Angular momentum is there also. Similarly, mass will be converted into mass distribution. Velocity will be converted into angular speed. So now angular momentum is defined as I times the omega. So that will be, call it as the angular momentum. Again, since momentum is conserved, this quantity also a conserved quantity. So how we identify it is conserved. Simple example that you can think may be here. So you see that in here I have the person that have the weights and sitting on the turnable table, rotational table, that he try to bring mass back and forth. By doing back and forth masses, what basically he is doing? He is changing moment of inertia. So moment of inertia in here, that means I in here is smaller because he have masses close to the rotational axis. When the masses are far away from the rotational axis, that means he has larger moment of inertia in here. Then since I times omega is the angular momentum, right? Angular momentum is equal I times omega. It keep constant. That means I times omega is keep constant. That means since I have greater I here, I should have a smaller omega in here. But here, I should have a greater omega. That means if you need to do more rotation, speed more, that means you need to keep masses together or your hands together, you can move it faster. So if you bring it away from your body, then it will be slow down the motion because of the angular momentum is conserved. Okay, so like another video that you have it in your yes, that in your demonstrations video. This is the angular momentum video that you guys can watch later, but I'm just going to probably show it in here in very small screen. So now let's see. Okay, so let's see. So slower, faster. Okay. So let's see, he's probably going to do it one more time. Probably not. So this is the only place that is big. So slower, faster, slower, and when bring it together, faster. Okay, you can take a time and watch that when you have time. Okay, so now there is some other application, probably diving and long jumping. You can move it faster by doing your body together. That's the application of angular momentum. Okay, so that's it for this section. And again, make sure you attend the recitations and do the homework and the worksheet problem as much as possible.